You ever get the feeling the world is just full of little mysteries? Well, today, we're going to be data detectives. We're going to grab our toolkits and see how looking at the world in a certain way can help us crack the code of all sorts of everyday puzzles.
So let's kick things off with our first case. I mean, this is something you deal with every single day, right? But have you ever really stopped to think about it? How in the world does your inbox know how to filter all that junk out from the stuff you actually want to read?
You know, to solve a mystery like this one, we can't just guess. We're wading right into the case of uncertainty. See, the computer isn't 100% sure that an email is spam. It has to make a really good, educated guess. And to do that, we need some special tools designed to help us think clearly when we just don't have all the facts. And here's the secret. The tool that makes this all work isn't some kind of crazy, unknowable magic. Nope, it's actually a branch of mathematics that gives us a solid, logical way to handle doubt and chance. It's the language of probability.
Okay, so let's pop open our detective's toolkit. The very first thing, the most fundamental tool every data detective has to get good at, is this language of chance. Getting the basic rules of probability down is the foundation for everything else we're going to do. So what even is probability? Really, at its heart, it's just a way to put a number on the idea of maybe. Just picture a scale that goes from 0 to 1. 0 means no way, not gonna happen. 1 means, oh yeah, it's a sure thing. All the really cool detective work, that all happens in the space right between those two numbers. And here it is, the first rule in our detective handbook. Now, it might look simple, but this little formula is so powerful. That P of A you see, that just means the probability of event A happening. To figure it out, we just take the number of ways we can get what we want, say rolling a 6 on a die, and we divide it by the total number of things that could possibly happen. For a die, that's 1 win divided by 6 total sides, which gives us a probability of 1/6. Simple, right? And now, let me show you a fantastic little shortcut. It's called the complement rule. Basically, the formula just tells us that the probability of something not happening is just 1 minus the probability that it does happen. So if there's a 70% chance of rain, you instantly know there's a 30% chance it won't rain. It's a really simple but super useful trick to have in our toolkit.
All right, so we've got the basics down. But you know, real detective work is never about looking at just one clue by itself. The real magic, the thrill of the case, happens when a new piece of evidence lands on your desk and totally changes how you see everything.
And this is where we need our next tool, conditional probability. Let's go back to our spam filter. Okay, so the chance of any email being spam is one thing, but what's the chance an email is spam given that it has the word lottery in it? Whoa, see? That new clue changes the odds completely.
Now this formula might look a little intimidating, but it's really just the instruction manual for connecting clues. It calculates the probability of A happening, given that B already happened. It's the mathematical engine that lets our investigation get smarter and adapt every time a new fact comes in. And this whole idea of updating what we believe based on new evidence, it leads us to what is, I'm not kidding, the absolute crown jewel of the data detective's toolkit. This is the powerhouse behind so much of modern data science, everything from machine learning to search and rescue.
Everyone, meet Bayes' theorem. You'll see it uses that conditional probability we just talked about. This thing isn't just a formula. It's a recipe for how to learn from the world. It takes what we originally believe, our prior, mixes it with the chances of seeing some new evidence, and spits out an updated, smarter belief, the posterior. This is the logic our spam filter uses to get better and better at its job every single day. And trust me, this is not just some abstract theory. This single idea powers so much of the world around us. Of course, there's spam filtering, but it's also absolutely crucial for medical diagnoses, it helps guide search and rescue teams, and it's basically the bedrock of all modern AI and machine learning. It's everywhere. So here's the thing, detectives almost never get to see the whole crime scene, right? They find one small clue, a single footprint, a tiny fiber, and from that tiny sample, they have to make a huge, bold claim about the big picture. They have to make what we call an inference. And guess what? There's a whole scientific field dedicated to doing this the right way. It's called inferential statistics. It's basically the rule book that gives us the methods and, just as importantly, the safety rails for making that big leap from a small piece of evidence to a grand conclusion.
Okay, we've collected our clues, we've made our inferences, and now it's time for the final act. It's time to walk into the courtroom, present our evidence, and finally deliver a verdict. You see, in the courtroom of data science, every single case starts with a showdown, a face-off between two competing stories, two rival theories, each one trying to explain the facts. On one side, you have the null hypothesis. Think of this as the presumption of innocence. It's the boring status quo theory. It basically says, nothing new or interesting is happening here. In our case, that would be, this new spam filter is no better than the old one. But on the other side, you've got the alternative hypothesis. This is the exciting claim, the theory that we found a new discovery. This one shouts, hey, this new filter is actually better.
And to decide between these two stories, data detectives follow a really clear 4-step process. First, you state your two competing theories. Second, you go out and collect your evidence, your data. Third, you weigh that evidence. And finally, fourth, you make a formal decision. So how exactly do we weigh the evidence? Well, we use a cool tool called the p-value. But don't worry about the name. All you need to know is that the p-value is our surprise meter. It asks a very simple question. If we assume nothing has changed, that our filter hasn't improved at all, what are the odds we'd see results this good just by pure random luck?
And this, right here, is the smoking gun. A really, really small p-value means your results are super surprising. They're so unlikely to have happened by chance that it makes you seriously start to doubt that boring old presumption of innocence. It's a huge hint that you might be onto a real breakthrough.
But how small is small enough? Well, in a lot of scientific fields, the general agreement, the line in the sand, is this number, 0.05. If your p-value comes in at less than 5%, researchers will often call their finding statistically significant, and they'll feel confident enough to reject that boring old null hypothesis.
And just like that, we have our answer. By using this whole structured process, starting with probability, updating our beliefs with new evidence, and then formally testing our theories, we can go from total uncertainty to a confident, data-driven conclusion. We've cracked the case of the spam filter. We just put together a pretty basic, but honestly an incredibly powerful toolkit for thinking clearly in a very uncertain world. It's how we find the signal in all the noise. So I guess the only question left for you is, now that you have the tools of a data detective, what mysteries are